Black holes, one of the most baffling and peculiar phenomena in the universe, remain the focus of intense examination and interest among space experts and physicists alike. These celestial objects, defined by their monstrous gravitational pull and the total absence of light emission, represent a limit beyond which the known laws of physical science no longer apply. As Albert Einstein first hypothesized in 1916 as a consequence of his theory of general relativity, black holes were only theoretical until technological advancements allowed for their indirect detection during the 20th century. The turning point came during the 1960s when astronomers studying the Cygnes group of stars accidentally discovered an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star, orbiting an invisible companion, defied regular explanations, until it was revealed to be in a gravitational relationship with a massive black hole, Cygnes X1. The discovery of Cygnes X1 provided clear evidence for the existence of black holes and marked the beginning of a new era of investigation into these cosmic enigmas. Located about 6,000 light-years from Earth, Cygnes X1 is incredibly dense and exerts a gravitational force so intense that not even light can escape its grasp. This defining feature earned it the name black hole, encapsulating the essence of these mysterious objects. Subsequent research has discovered numerous black holes scattered throughout the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million. Despite their elusive nature, which makes direct detection challenging, astronomers have identified several candidates within our galaxy, ranging from stellar mass black holes formed from the remnants of massive stars to supermassive black holes located at the centers of galaxies. The gravitational influence of black holes extends far beyond their immediate vicinity, shaping the evolution of cosmic structures and influencing the fate of surrounding matter. Objects that venture too close to a black hole face a fate determined by its relentless force. They are drawn inevitably toward the event horizon, the final boundary where they are subjected to extreme tidal forces and ultimately consumed by the singularity at the black hole's core. This catastrophic interaction, known as spaghettification, is the extreme manifestation of a black hole's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes stretched to its extreme, contorting it into a filamentary shape resembling strands of spaghetti. The forces exerted by the black hole overpower the internal bonds keeping the object intact, causing it to disintegrate into a flow of matter that, in the end, merges with the singularity. Despite the allure of black holes as laboratories for testing the limits of physical theory, they remain shrouded in intrigue. The quest to unravel their secrets continues, driven by a desire to understand the fundamental nature of spacetime and gravity itself. In the vastness of the universe, black holes stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the boundaries of human knowledge. Despite the tremendous distance separating us from the nearest black hole, roughly 1,500 light-years away, questions and concerns about their potential impact persist. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a black hole, specifically M87, located at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of black holes and their elusive structure. The visual data revealed that black holes have complex layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and image stitching, scientists identified three distinct layers within a black hole. 1. The event horizon, the outermost layer and crucial boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable fall into the black hole's depths. 2. The photon sphere, the second layer, where light travels in perpetual captivity around the black hole. Any photons that venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the black hole's cosmic embrace. 3. The singularity, at the heart of the black hole lies this third and final layer, where physical laws break down entirely. The familiar laws governing the universe cease to apply, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity of black holes and their inherent variability present significant challenges to our understanding. While they share a common three-layer structure, each black hole exhibits unique characteristics and behaviors, defying simple categorization. As such, traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. Indirect observation remains the primary means of studying black holes, as direct investigation is rendered unfeasible by the immense gravitational barriers. Launching probes into black holes would inevitably result in their destruction, crushed into obscurity by the relentless forces at play. Nevertheless, researchers persist in their quest to decipher the secrets of these cosmic giants. Various theories, ranging from the collapse of stars to cosmic dynamics, offer tantalizing glimpses into their behavior and origins. In particular, NASA's study of the cosmic center of M87 revealed compelling evidence of a superenormous black hole exerting its gravitational influence over vast cosmic scales. Despite these challenges, the pursuit of knowledge continues unabated, driven by humanity's inherent curiosity and thirst for understanding. While the black hole mystery may defy simple comprehension, the steadfast dedication to scientific investigation promises to illuminate the darkest corners of the universe, unraveling the profound secrets hidden within. Roy Kerr's groundbreaking work in 1963 presented a paradigm-shifting perspective on black holes, proposing a revolutionary theory of rotating black holes that defied conventional understandings. Central to Kerr's model was the concept of the ergosphere, a region surrounding the black hole where opposing forces collide and balance collapse by gravitation, preventing matter from collapsing further inward. This novel domain displayed curious deviations from traditional physics, hinting at the profound mysteries concealed within black holes. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure is a potential gateway through spacetime, facilitating communication between distant regions of the universe, or even parallel universes. The idea of wormholes stems from the intricate interplay between reality as described by Einstein's theory of general relativity. In this framework, existence is woven together, forming a four-dimensional fabric known as spacetime. Massive objects warp this fabric, creating gravitational fields that affect the motion of surrounding matter. Wormholes essentially act as shortcuts through this cosmic fabric, connecting distant points in spacetime and potentially enabling rapid traversal over vast cosmic distances. Moreover, the theory of general relativity proposed by Einstein imposes fundamental constraints on the formation and sustainability of such constructs. For a wormhole to remain stable and traversable, it would require the presence of exotic matter, a theoretical form of matter with negative energy density and pressure. This exotic matter, while mathematically conceivable, has yet to be discovered or produced in quantities sufficient to support a wormhole's structural integrity. Even if such matter could be harnessed, the wormhole would face threats from quantum instabilities. Minute fluctuations could trigger collapse, making any passage through it hazardous, if not fatal. These considerations have led many physicists to regard wormholes as fascinating theoretical curiosities rather than imminent engineering possibilities. Yet, the allure of wormholes persists, especially in the realms of cosmology, quantum gravity, and science fiction. They invite speculation about time travel, faster-than-light communication, and multiverse exploration, concepts that continue to inspire both academic research and popular imagination. Recent advances in quantum field theory and loop quantum gravity have opened new doors in understanding the intersection of general relativity and quantum mechanics. The concept of Hawking radiation, proposed by Stephen Hawking in the 1970s, further complicated our understanding of black holes. According to this theory, black holes are not entirely black. Instead, they emit radiation due to quantum effects near the event horizon. This revelation had profound implications. If black holes emit radiation, they must eventually evaporate over astronomical timescales, potentially leaving behind nothing, a notion that contradicts the classical idea that nothing can escape a black hole's grip. This led to the now famous black hole information paradox, which questions whether information that falls into a black hole is lost forever or somehow preserved. Resolving this paradox has become one of the greatest challenges in theoretical physics. Competing theories suggest different outcomes. Some argue for information conservation through quantum entanglement or holographic principles, while others propose that new physics beyond the standard models of gravity and quantum mechanics must be developed. One such proposal is the ADS-CFT correspondence, a conjecture in string theory suggesting that a gravitational theory in a higher dimensional space, like that of a black hole, can be described by a lower dimensional, non-gravitational system on its boundary. This duality offers a promising framework for addressing the information paradox and understanding the quantum structure of black holes. In tandem, technological advancements continue to refine our observational capabilities. Instruments like the Event Horizon Telescope, EHT, which captured the historic image of M87's black hole, represent a new era in black hole research. Future projects aim to observe Sagittarius A*, the supermassive black hole at the center of our own Milky Way, with even greater clarity. These observational efforts not only confirm theoretical predictions but also provide new data that can challenge or refine existing models. As we continue to explore the cosmos, black holes serve as crucibles for the most fundamental questions in physics, about the nature of matter, energy, space, time, and the limits of human understanding. Far from being mere cosmic vacuum cleaners, black holes are proving to be gateways to deeper truths, possibly revealing the quantum underpinnings of reality itself. Their study may one day bridge the chasm between Einstein's geometric universe and the probabilistic world of quantum mechanics, bringing us closer to the elusive theory of everything. The speed of movement through spacetime, suggesting that even if stable wormholes existed, they might not facilitate faster-than-light travel, is an important part of many sci-fi narratives. Despite these impediments, the enticement of wormholes persists as a shining example of scientific interest and exploration. The concept of the wormhole, named after its pioneering scholar, embodies the tantalizing promise of cosmic portals and alternate realities, inviting humanity to contemplate the mysteries of the universe and ponder the infinite possibilities that lie beyond. The quest for a unified theory that reconciles the seemingly disparate domains of gravity and quantum mechanics has spurred the search for a theory of everything, a comprehensive framework capable of incorporating all fundamental forces and the universe's particles. At the forefront of this endeavor stands the renowned theoretical physicist Myoku, whose groundbreaking work has propelled the study of superstring theory. Superstring theory represents a dramatic departure from conventional ideal models, hypothesizing that fundamental particles are not point-like entities, but rather tiny vibrating strings. These strings, much like those of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its capacity to explicate enigmatic phenomena associated with black holes, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. Whereas superstring theory's elegance masks its inherent complexity, it nevertheless necessitates the existence of additional dimensions beyond the familiar three spatial dimensions and one temporal dimension. These extra dimensions, being out of direct observational view, present a significant challenge to human intuition. Despite this, useful models, like the analogy of fish living in a two-dimensional lake, provide a glimpse into the elusive nature of these higher dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales, yet their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing profound connections between dynamic patterns in mathematics and physical phenomena. Indeed, the pursuit of a theory of everything has catalyzed the convergence of disciplines, shedding light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific potential, superstring theory remains an untested framework, in need of experimental validation. The elusive nature of extra dimensions presents a formidable barrier to such verification, relegating superstring theory largely to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing them on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised at the beginning of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum black holes has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts to tackle this riddle, a live solution has remained beyond our grasp. This prompted Edward Witten, from the Institute for Advanced Study at Princeton, to describe superstring theory as 21st-century physics that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum black holes. Several groups of physicists have independently reported significant breakthroughs, revealing that string theory could offer a comprehensive solution to the problem, albeit within the more constrained context of two dimensions, as opposed to the entire 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing, with the complexities of the situation presenting substantial obstacles. The search for a unified theory of everything beckons us to probe the darkest corners of the universe's existence, where the boundaries between reality and theory blur and the secrets of the cosmos await discovery. The study of black holes carries profound implications for our understanding of the universe, testing our ideas of reality and raising fundamental questions about the nature of existence itself. The interplay between black holes and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. These celestial events, governed by the extreme laws of physics, serve as natural laboratories for exploring conditions that cannot be replicated on Earth. Through the study of gravitational waves, quantum radiation, and accretion dynamics, scientists gain unprecedented insight into the inner workings of spacetime itself. One particularly intriguing phenomenon is Hawking radiation, a theoretical prediction that black holes are not entirely black, but instead emit tiny amounts of thermal radiation due to quantum effects near the event horizon. This discovery bridges quantum theory and general relativity, offering a tantalizing clue toward a unified framework. Yet, despite its elegance, Hawking radiation remains unobserved, highlighting the vast gulf that still exists between theory and empirical evidence. Meanwhile, the potential synergy between superstring theory and loop quantum gravity continues to spark debate among physicists. While fundamentally different in approach, one relying on smooth geometries, the other on quantized loops of spacetime, some propose that both may be complementary views of a deeper, unified structure of the cosmos. The dream of synthesis, though distant, keeps theoretical physicists pressing forward, driven by a shared desire to decipher the code of creation itself. As our instruments grow more sensitive and our models more refined, humanity stands at a pivotal moment. The mysteries that once lay hidden in the shadows of black holes and curled-up dimensions are slowly being brought into the light of understanding. Large-scale experiments, such as those conducted at CERN and through satellite-based observatories, may soon offer crucial data capable of confirming or refuting the predictions of these bold theories. In the face of cosmic scale and temporal immensity, the human pursuit of knowledge becomes an act of profound courage and creativity. It is in the equations scrawled on blackboards, the beams of particles hurled through accelerators, and the quiet contemplation of physicists staring into the starry night, that our species reaches beyond itself. This journey is not just scientific, it is philosophical, spiritual, and imaginative. In our attempt to grasp the universe's origins and fate, we are also searching for our own place within it. The quest for a theory of everything is, ultimately, a quest to understand what it means to be part of this grand, mysterious, and beautiful cosmos.